Hi, my name is Edward Turner, and this presentation covers my course project, which was a comparative study of two multi-output forecasting strategies, one being the multi-output regressor, and the other being the regressor chain, and with its application towards retail sales forecasting. This work uses the Walmart's M5 dataset and evaluates how each method performs when generating a 28-day demand forecast. I'll walk you through the motivation, the dataset, the methodology, the experiments, key findings, and insights for real-world development. So, accurate multi-step forecasting, which is essential for retail operations because it impacts, several things such as inventory levels, labor planning, logistics scheduling, and overall profitability. All those being important, but also difficult to uh, actually predict. Now, reasons being, you have retail data that's noisy. Sometimes there's strong promotional and seasonal effects. And traditional time series models like ARIMA struggles with that level of complexity when you have multiple other features that are incorporated. So that's why machine learning models, especially gradient boosting trees, offers a significant advantage. But the question is, how do you structure a multi-step forecast with this as a base model? And normally this is overlooked. Uh, this study is going to investigate two competing approaches, and as I mentioned, it's going to be the M output, aka the multi-output regressor, versus the regressor chain. Now, retailers often need to forecast for many days at once, as the example being the 28-day look ahead for supply chain and staffing decisions. Choosing the wrong forecasting strategy introduces unnecessary risk, especially when errors compound across horizons. Understanding whether it's better to model horizons independently or sequentially has direct implications for cost savings, agility, and overall deployment stability. And so the overall hypothesis uh, is what we're going to consider throughout this entire study, which being, does the regressor chain outperform the multi-output regressor? And sequential dependencies will reduce errors. That's the hypothesis in a research question. Again, it's important that we do so, and there's direct implications on cost savings, agility, and deployment stability. So these are things to keep in mind. And so therefore, finding out the actual proper approach is going to help us alleviate those potential problems. So the data set that I use is the Walmart M5 data set, which includes daily sales for thousands of products across multiple stores and states. It also includes meta information for items. It includes price histories. It includes detailed calendar features that includes holidays and special events. This data set is ideal because it reflects real world retail noise, intermediate demand patterns, and strong external drivers. Now, this is where I'm going to switch to my repository for showcasing some of this. However, the methods that we use for the feature engineering component is going to include lagged sales over a 7, 14, 28-day period, rolling means, standard deviations, calendar encodings, and holiday flags. Both these multi-output strategies use the same light gradient boosting model as the base estimator to ensure a fair comparison. And hyperparameter tuning was done, specifically Bayesian hyperparameter tuning was done using Bayes search CV with identical search spaces. And then all the experiments followed a strict temporal validation to prevent data leakage. So now I'm going to showcase the code. So first is how we manage the data. So obviously, with the way I was doing things here, because we want to get the data, which is normally in not long format, but wide format, and create a long format structure, but still with a cascading 28, not cascading, but a trailing 28 days for any of the features that we're generating, and then naturally the forward, right, to look forward 28 days. And so this means of loading the information for calendars. This is transforming the data into a long format perspective, just casting things to different types, sorting values, making sure that things are as they should be for easier management when it comes to the trailing effects. These are calendar features, which we did include sine and cosine since we're trying to capture the nonlinearity aspect, right? When it comes to the month and the day of the week, because we know there might be uh, during the week fluctuations and also monthly fluctuations. We want to capture that. And then these are the lag features I was referring to earlier. So we capture lag mean, standard deviation, median, mean, max, sums. Look at the quartiles from the 25th and 75th perspective. We also look at the null counts as well, just to see what the data looks like from a null perspective, because there are some columns that were null. Uh, Holiday counts, weekend counts, looking at other different, we're calculating different trends as well in the data, and we're doing that across the sale price. So we just across the sale price and our particular target column, which is the sales count. So we try to look at the lag of the sales count and seeing if past sales is going to lead us to more accurate future sales, and that's what our focus is. Now, because of the way this is done, it could very well easily explode from a memory perspective. And so I batched it and I used Dask to help orchestrate the parallelization of the data. And so this is one of the functions that incorporates that. But we calculate the calendar features, we get the categorical features, and we calculate the lag features, and then we execute all this in parallel on the rolling features for a singular group. As you can see, we're computing and having a progress bar so that we can track it along the way, and then we concat everything together and save it to Parquet. And this is within the batch file. So we're doing is we're creating a batch of this data and then saving it. And again, that's a means of controlling the overall data volume from an input RAM perspective. And then we take that data and we start performing our different types of data splits to generate then the X and Y data because we have to generate the X and Y data. And that's what's done here. So we generate the X data, generate the Y data, and then that gets saved as well as you see the Parquet. And that's a high level. The rest of this is just regular Dask stuff, management of the methodology. These are parameters just to show you what I was looking at. You have to look back at 28 days. You have a forecast horizon of 28 days. You have rolling windows of 7, 14, 28 days. We have lag features of 1, 2, 3, 7, 14, 21, 28. So we're looking at the last day, last 2 days, last 3 days, last week, last 2 weeks, last 3 weeks, last 4 weeks. And we try to make sure we have a minimum number of 56 days for training purposes. So this means that we'll end up clipping records that don't have in a group consecutive 56 days. And that's just, and that's just to make the split because we're going to look at 28 days in the past, 20 days in the future. So we need to make sure that we have enough data for each of those. These are group by columns because we're going to group by the item and store. And then we have different categorical columns here that we want to make sure we capture and encode properly. So again, as I mentioned, very straightforward. It just runs in parallel, and those are the features that we generate. Next is the ensembling of the models. And so I went through a few different approaches because as you can see, I had even had XGBoost as part of the column as the name of the file. I was originally get XGBoost and light gradient boosting, and it would have been nice to incorporate the two because they both create the trees differently. You have XGBoost being more depth leveled, and so it goes basically according by tree the tree base generation level by level. Meanwhile, light gradient boosting is really more optimized at the leaf. So it's going to try to it's going to create the trees at the leaf level versus at the I guess depth level, if that's it. You have basically a difference of depth, search and depth-based search and breadth-based search. And I guess XGBoost is more keen to breadth-based search, while Lightning Boost is more depth-based based on the leaf versus level breakdown. But either way, this is the file for generating the training data. So as you can see, I get all the data. I read everything in. I make sure things are encoded properly based on the categorical columns that are there. And also I do a simple imputation. Uh, Now these are the parameters I use for the hyperparameter tuning. I look at the number of leaves I use for light gradient boosting. The maximum depth, which is set from 3 to 10. That's fairly conservative. We could have expanded more, but I wanted to keep it at a reasonable level. But max depth of one might have been decent, but again, it's not necessarily needed. We have learning rates of 0.01 to 0.3 log uniform distribution. I could have set this to a lot lower, so that way we can kind of capture longer trainings that might have led to maybe a more performant model, but for this particular scenario and project. I didn't want to go into that level of detail, but we could have done that. We have the number estimated as being 100 to 1,000, standard, standard assumptions. And minimum number of child data points in the sample. And that's normally used to help with splitting a node into leaves altogether. And you have subsample, which refers to the randomization of the number of rows that you're going to subsample over time for each tree. We have column sample by tree. And so this is going to essentially refer to every time we create a tree, what's the sample of columns we're going to use? And it's going to randomize that. So kind of think of like an extra trees type methodology here. And then regulation parameters for alpha and lambda that really just helps mitigates the potential overfitting that could happen. And so we do make sure that, and it's done at the split level as well, when it comes to optimizing for the min gain or max gain, excuse me, from the split. And so we're going to have some regularization parameters to make sure that things are split accordingly without overfitting. But yeah, this is that's the parameters. And so this is the temporal train test split. So you can see right here we have the X train, which we look at everything. Well, let's start with the X test. So we look at the number of records. And remember, this is supposed to be sequential, so we already sorted by the day. And so we're just looking at, well, what's the number of records in the test set that we want to use? We use the last X number of them for the test. Then we look at, well, everything before that is going to be the train validation split. And then we look at, well, based on the number of data points remaining, what's the validation size should be. And so everything from there, the validation point up to the number of test points that's going to be used for the validation set. And then we have the train right here. And this is just to really help us understand how well we're doing across different model splits. And so each of those are returned. And then we have the actual multi-output model. So this is where we're going to have the Bayesian search wrapper on top of the estimator. We're going to specify the search space here, and then specify what's the scoring mechanism we're going to have, which is going to be the negative mean squared error, which is the closest we can get to the root mean squared error from this use case. And that would be the multi-output regressor. And so this is going to essentially break out into 28 different light gradient boosting models that can be trained in parallel. That's going to optimize for just day one, day two, day three, day four, so on and so forth, without using day one, day two, three predictions for day four, five, six, so on and so forth. And then this is the regressor chain. Again, very similar. The difference, though, is that we're swapping out the regressor chain here. And so now we're assuming that the output from day one is going to feed into output day two, day three, day four, and so on and so forth. This is the model evaluation code. I calculate the residuals right here. Then this is the creation of the root mean squared error across all the rows. So we're looking at we want to make sure we're looking at the root mean squared error per day because we want to look at how well does per day. And that's the same thing here with the mean absolute error. This is going to be a per day estimation. And then this is the mean absolute percent error, which I calculate here, but we don't have to focus necessarily per se on this particular metric. And then we also calculate the R2, which is going to be, as you can see, across the per day. And those metrics are calculated here, and that's the evaluate model method. And the compare model method, where we actually just compare each of the metrics and create a comparison report. Uh, and then we save everything to results, and which would basically mean we're saving everything to a CSV file and so on and so forth, so it can be used to create the charts that we'll look at in a few moments. And then this is the rest of the remaining configurations and the main script or main function that we execute to get all of the values for the models. And this is where we also get the best estimator and also the best configuration or some of the best the best parameters from the Bayesian optimization search. So we loop through each estimator and we look at the best parameters and best score for those parameters. And yeah, so that's essentially the code here for the overarching model code, and that's the methodology. Uh, and from the figures, again, this is the representation of what we're doing with the models and how we're comparing. But you're going to have day one, day two, day three, day four, that's going to be predicted individually for the multi-output regressor. So it's assuming that each day is unique and separate. And then you have the regressor chain, which is going to predict day one and use that to predict day two, use it to predict day three, and so forth to day 28. Now, there's a few pros and cons for this. Unfortunately, while I was hoping to win, loss. But we're going to have better accuracy with the multi-output regressor, treating each day independently versus the sequential, which is it's supposed to hopefully use the sequence of the sales to predict the next following day. But because of error propagation, the predictions got worse over time, which is unfortunate. But that's the final output from the model. Now, when it comes to the errors again, the metrics as I described earlier, you're gonna have the root mean squared error here, as you saw multi-output, or at least that's what I described the multi-output in the report. The multi-output model was better in the sense had a lower root mean squared error average across all of the horizons. Same with the mean absolute error. It's just substantially lower, as you can tell, by like half the amount. Uh, this is also a lot better too. As I mentioned earlier, we don't have to focus on this metric 100% per se, but as you can see, it's substantially a lot better in comparison. But then the R2 score, which is what we're more familiar with, as we saw, the average ended up being 0.389, which is still not perfect, but it's a lot better than zero, which is what the average was across all the horizons for the regressor chain. And then these are the horizons over time. This is what you can kind of see. The regressor chain, the root mean square got higher over time, and then it kind of stabilized a little bit. But the multi-output, it also slowly got higher over time. And then by day 21, it dropped and just got better, which is very interesting. Very much similar to the mean absolute error, as you can see. The regressor chain went up and then stabilized versus the multi-output where it slowly crept up, which makes sense because you have predicting things further out is more difficult to do, but This is much better, of course, in comparison to the regressor chain. And then the R2 score, as you can see, kind of stabilized. It went down a little bit for the multi-output, but stabilized, hovering around 0.4, 0.39, maybe around up 0.4. But the regressor chain, it just got worse and worse and worse. And you got to the point where the model was not really that performant at all for the regressor chain. It was just not. And then this is just a description of the gap. So the root mean squared error, so the gap between the two got larger and larger over time. Uh, and even though we're saying the propagation began at day 7, that's where it was more substantially noticed. But you can even tell a little bit earlier that it was slowly going up. But it was substantially noticed at this point where it just went exceedingly high. And that's the same as you see here. This is the bar chart of the difference, which is pretty bad over time. And then you have uh, the rest of the descriptions, the rest of the summaries. You're gonna have again the winner being the multi-output regressor. Uh, why multi-hydrogen wins. It assumes each day is independent, so therefore there's no error propagation. Each model was optimized separately. So even though you had that for the regressor chain, but because the error propagation, the diff between the predictions and the next day was not predicted properly for the model. So it didn't predict that, which is assume that day 1 is predicted perfectly. So therefore day 2 should be predicted, with X number of perfection and so forth. So again, that was uh, an issue for the regressor chain, but not for the multi-output. Now you also win from the multi-output perspective because you have parallelization across each of the days. You don't get that for the regressor chain because it has to be that's forced to be sequential. And then you have retail sales characteristics. So we did still capture some weak level of sequential dependencies, and this is from the lag features that we captured. So even though we weren't able to do a lookout where you had day 1 helping to predict day 2, you did have previous days 28, 14, 7, 3, 2, 1 that helped with understanding uh, whether that seasonality I was capturing those previous lag days would impact the future days. And so you did capture that still. You also had what's called Occam's razor, simpler is better. And in this case, training several different models to predict an individual day independently is simpler than trying to train a sequential model. Now the error propagation, as we described before, it got worse over time. By day 1, the error was 0.73, then it was 0.93, and then 1.01. And then by day 28, it was 0.99, so the error wasn't substantially higher by day 14, but the R2 score was negative 0.13. So again, it's very bad. And for the retail use case, where data noise is high and sequential dependencies are weak, uh, the independence that is seen from the multi-output regressor is very advantageous and something we should definitely consider. And then we have some practical implications. We have some things that we could look in the future. So we have, again, for the multi-regressor, this is great for the production deployments. We're going to have high value retail forecasting. We're going to also achieve higher accuracy as a result from this independency as assumed. And there's also large scale implementation. So we can deploy this actually as a separate Spark function. So the way I did with multi-output regressor was simple enough, right? Because we were able to do this with as scikit-learn. But if we wanted to deploy this using Spark and then deploy against the Spark cluster, we can do that. And we just predict, use different predict columns. We could have easily created a pipeline object or a column transform object, or even just several different Python scripts that would run against day 1 and then another one for day 2 and then day 3, and that would be 28 different tasks inside a DAG that would then be executing against the Spark cluster, and that would scale that would scale a lot more than the regressor chain. It'd scale a lot more than what we have right here. This is just done on my computer. So there's a lot of implications when it comes to using the multi-output regressor. We can run this a lot faster. Now, why we want to avoid the regressor chain? Very straightforward. Error propagation. It's not suitable for retail sales if we have that seasonality that or the data noise that just exists, and the computational cost because it's all going to be sequential. And so one of the key insights is independence over dependency modeling and for specifically retail demand forecasting. Uh, Now, in conclusion, the hypothesis was rejected. Regression chain does not outperform the multi-output regressor in any setting. Uh, Multi-output regressor delivers better accuracy, better stability, better operational reliability. And for hypermarket and omni-channel retail forecasting, this strategy in particular is recommended for production grade pipelines. Now, for future work, we may explore hybrid models or SQU or SKU level uh, strategy selections and probabilistic forecasting. This could be something similar to quantile regression, where we look at the uh, credible intervals that we normally use within Bayesian statistics to predict the likely hood of a sale falling within certain bounds. And that might be more useful over time, is to predict the intervals, and that gives us a better understanding what our estimations are versus trying to do a point estimate. Point estimates are difficult over time, but we may be able to do better with a quantile regressor. So that's the end of my report. Thank you very much for reviewing my project. If any questions about the methodology, the Python code, Bayesian optimization, or any model deployment considerations, I'll be happy to discuss them.